It is time right now. We do have one more company. Maybe we could, who knows much about quantum computing? Oh, okay. Who wants to learn about quantum computing? All right. So if people do need to leave hard stop at 2, obviously please head out. Otherwise, we're very lucky to have Matthew, who flew in from Sydney this morning. Peter, do you want to get up and also, wear your other hat, head of Quantum Australian? Okay, great. So, and thank you, Rick, for coming. Great to see you. Thank you, everyone who I don't know who had to leave. This is a company that we met. Bill and I were here for South by Southwest Sydney. So in October 18th, it was a Saturday. And, it was kind of a full week back, just like West Tech Fest, right? It's like every big do all day long in Sydney doing South by Southwest events. And then I didn't know what this was. I just, basically it was kind of just supposed to be a field trip, or we're going to lab visit. We're going to go check out this company. Yeah, like we're just gonna learn. And I remember the night before, people were like, "Well, how much do people know about quantum computing?" And I was like, "Well, watch the YouTube Quantum Computing for Dummies," right? So we have good questions to ask. We didn't really know exactly what it was about. Ended up being a 3.5 hour deep dive. First of all, Bill walks into the room. He starts whiteboarding directly with Dr. Michelle Simmons, who's one of the leading top 5 quantum expert in the world. I think the rest of us are just kind of watching this. Then we're streaming on Gigaverse, was the live video streaming platform that we invested in, because it was, and if anyone does want to see that meeting outside of some of the confidential financials, there's a company called Gigaverse. And if you go to ACTAI Global and you do it in the next, let's say, 48 hours, if we'll approve you, and you can actually see the meeting where Bill is asking, and everyone, but Bill really leading the questions, obviously as the first employee at TSMC, looking at the quantum space for the last 3 decades, and even weeks before saying, "Oh, I think it's kind of commercially a bit early," then meeting Dr. Michelle Simmons and kind of, at the end, kind of changing a lot of his mind. So with that, Matthew, why don't you give a quick intro on yourself and say where Michelle is, why she couldn't join us today, and then, yeah.
Sure thing. Well, thank you for having me, Amanda, and thanks for sticking around. I realize it's the middle of the afternoon, and I'm about to talk to you about quantum computing. So, my background is actually as a technology investor. So, I've spent my career in venture capital and private equity. So I've been beginning in investment banking. I was on the founding team of a venture capital firm in London. I was there for over a decade, and we actually ended up listing those funds, which were cornerstone by BlackRock, on the London Stock Exchange. I was the chief financial officer and chief investment officer there. That was back in 2021. I subsequently spent a couple of years in private equity, buying businesses in the UK. But I'd always had personal interest in what was theoretical physics once upon a time and what turned into quantum computing. And as a result, I was working with some quantum computing companies in the UK, which is how I met Michelle, and I met Simon, who's our chair, who's the former CEO of Arm, which is a chip architecture company, which is not well known, but extremely well regarded in many of the chips which are in your pockets today. Um, and they convinced me to move down to Australia, and here I am in Perth. So I live in Sydney, and the company's based at UNSW. And Michelle, unfortunately, can't be here today. She would love to be, but she's actually in Belgium. She's at IMEC, which is the world's leading research foundry. So while I'll go on to talk to you about what makes us special as a business in terms of the fact that we make our own quantum chips, we can't do it all ourselves. And so in order to make the computer, we need people who build what is known as the packaging around our chips. And IMEC are the world leaders at that. So we have a number of our management, including Shell, out there in Belgium, furthering that relationship and getting the packaging sorted.
Great. And before we jump into Michelle's background, why don't just give a 101 on what is quantum computing and why does it matter to everyone here in this room?
Yeah. So do you know one of the things which I think I listen to physicists talk, and they talk about things like entanglement and superposition, and they try and explain what that means in a few sentences, and I just never think it really works. So something which I'm personally very fascinated in is, so what does quantum mean as a word? So you see it in popular culture, or you hear about it in popular culture. You heard more about it in a business context. And ultimately, it just means things which are very, very small. And one of the things which I think is just fascinating about life is that the big world, the world that you can see outside and between ourselves, works on a set of rules, Newtonian physics. And then the very, very small world, the world of atoms, works with a completely different set of rules. And it's those set of rules that need to be taken advantage of in a computing sense and will deliver new computing powers. So those new computing powers will deliver parallelism far, far beyond the GPUs of NVIDIA. Now, it won't be useful for everything, so they won't be in your pockets, but they're going to be exceptionally good at solving very, very complicated problems like many body problems. So if you think about your body is a quantum system made up of atoms and molecules interacting. In order to simulate that, you need something which is very good at simulating many body problems. Classical computers can't do it, won't do it, they'll never be able to do it. You need a quantum computer for that. And that's what we're building.
And what are some of the use cases that you think will come to market soon? Like, give some examples for people of what's not solvable today that you think will be solvable through quantum computing.
Yeah, great. So uh, silicon quantum computing is a totally unique business insofar as we make our own chips. So it's just talking about the fact that that quantum computing and quantum refers to something very, very small. Now, silicon quantum computing is in many ways one of the world's leading precision engineering businesses. We make, we fabricate semiconductors at 0.13 nanometer scale, atomic scale. And because we can do that, we think we'll win the race to delivering a commercial scale quantum computer. But in the meantime, we can also make application specific devices which can deliver value today. So quantum machine learning, something that we call the watermelon, is a chip and a system that we've built, which is deployed within Australian Defence. Telstra use it, CBA use it, a couple of high frequency trading businesses use it to leverage quantum effects to deliver what we call quantum features back into their classical machine learning to improve that. And so that's something which is available today. But looking forward to the future, one of the reasons why quantum computing has become popular amongst journalists and big business is its potential for factorizing large prime numbers, which is a problem for cybersecurity, for example. And so the world will need to move to post quantum security in sometime in the next sort of 5 to 10 years, which is very important. But something a bit less scary than that, like I say, are the pharmaceutical use cases. But one of the things which is also very, very, I think, cool is it will be amazing at developing new types of materials. So corrosion costs the world about $2.5 trillion a year, which is roughly 3% of global GDP. Now, a quantum computer isn't going to solve corrosion itself, but it will be able to simulate and help formulate better materials that we can use to be more corrosion resistant. And so it's a huge economic unlock by having this new compute power, which sits alongside GPUs and CPUs.
Izzy, talk a little bit about Michelle. She's very humble, but I think we should brag about her since she's not here because I don't know, like just talk about her background. I mean,
Yeah.
she is incredible, right? Like really Australian of the Year too, and yeah,
This is
inventor of many things.
Yeah, this is awesome because she'll absolutely hate this, but she'll never know.
She's not here, so it's
Yeah,
okay.
yeah, yeah.
We can brag about her.
There's a camera, I just noticed.
No, yeah, I know.
I won't explain quantum.
Yeah. So Michelle Simmons, so she was born in the UK and grew up there, ended up at Cambridge at the Cavendish, which is a famous lab there, got frustrated by all the fusty, buddy-duddy academics and moved to Australia. Because she saw the opportunity to build something great here. She saw the collaborative spirit of Australia and has built this incredible research group, which turned into her company, and has delivered many world firsts and is the pioneer of atomic electronics. So she created the first single atom transistor. So first transistor once upon a time, is a Nobel Prize winning invention. Um, and beyond that, the first atomic scale integrated circuit. And of course, from that point forward, silicon quantum computing is world leading in its modality. And so there are many, many world firsts. But I think one of the things which, for me is absolutely amazing is, aside from the incredible physicists as a general sense that I get to come to work alongside each day, Michelle is most likely, I say most likely, I don't actually know this for a fact, but there's a good chance that she'll win a Nobel Prize one of these days. And so I wake up every morning, I'm like, great, it's time for me to go to work. It's the opportunity to work with somebody like that, may well win a Nobel Prize in physics one day and work on something which is truly going to change the world and arguably has already. It's just absolutely incredible. And it's just the most phenomenal opportunity.
You guys actually have a chip in market that is producing revenues, right? Talk about how rare or not that is in this space.
Yeah, it's a real tee up. So this is
That's what I'm here for. I want to make you guys look good.
So Watermelon is our quantum machine learning system, which businesses have been accessing via cloud, and in some cases, like Australian Defence, they bought a rack-mounted system, and it delivers these quantum features which help improve and certainly speed up AI in many contexts. So Telstra went to press about it 2-3 months ago, talking about the fact that it's sped up their deep learning model training time from a number of weeks to days, which in the context of the discussion of power that we've been talking about earlier on today is, of manifest value. And since that point in time, there's been a kind of beauty parade, which we're going to try to turn into a gravy train of data center investors and operators coming to our office to hear about the processor and what it can do for them. But we've got customers in all sorts of sectors, including actually mining. So CIMIC and Teeths are, is that how you say it? Teeths? Are interested, and we're talking to them about that to talk about predictive maintenance of various different machinery, and the applications for it are broad and cross industry. And so we're in the enviable position, sorry, of being able to choose our customers to a certain extent based on how big their R&D budgets are and whether they'll be able to be well suited to be on the commercial journey towards commercial scale quantum computing, where we can sell them ever greater and more powerful hardware as we look to build our revenues.
And just in the beginning of November, you're one of 11 companies, right, that reached stage B DARPA.
Yes.
Explain what that is and what's the significance for your company?
Yeah. So DARPA is the American Defense Research Projects Agency. And there's been a number of incredible technologies which have been not founded by them, but certainly seeded by them. I think, for example, GPS is one of the things which DARPA saw into operationalization. And they tend to engage with frontier technologies when they see the application in market for them. Now, with quantum computing, it's kind of been something which has been remote and always 10 years away, famously. People talk about it. And now DARPA's involved. I think they kind of see it as not 10 years away, and they see it as somewhere between 5 and 10 years away. It's coming, and in many ways, the processor like we have, which is Watermelon, is a good example of the fact that you can leverage quantum technology today to gain value and advantage as a business. But commercial scale, fully programmable quantum computing is coming soon after that. So DARPA created what's known as the Quantum Benchmarking Initiative, where I think it was 21 businesses got on to DARPA Stage A, which was roughly about a year ago. And then there's been this sort of down select since that point in time, where there are now 11 companies on it. So, out of all of the quantum computing companies in the world, Pretty much everyone will have applied for stage A. Not all of them got through to stage B, and I suppose I don't know. We were confident of getting through to stage B because we're one of the world's leading quantum computing companies. But of course, to have that validation and to have that support in the American market is critical for our business.
Maybe just talk briefly, like since we met you October 18th, right? Like you guys came out, she was presenting at NVIDIA's NTech, their internal engineering conference with the CTO and co-founder of PsiQuantum and the head of quantum engineering at UC Berkeley. Bill, I think, came to some leadership meetings. NVIDIA, I've helped set up some meetings for New Mexico and hopefully soon Colorado. So you guys can potentially look at manufacturing in the US as well, given tariff situations. You'll need to be manufacturing there. Talk a little bit like just, I mean, it's been such a short time that we've known you, and I feel like we've been on WhatsApp a lot. We have an SPV open for this company. The fund will, likely be investing. We haven't yet signed a term sheet, but and then there are a number of LPs in our fund who want to also invest directly. Just talk about just how quickly all that has happened, and maybe talk a little bit about some of what Bill's done with you in the short time.
So one of the things which I really wanted to say is that for all of you who are investors in ACTAI Ventures already or potentially...
By the way, I did not plan for him to say this.
It's absolutely amazing, right? So I'm a former venture capitalist myself, and I know good ones from bad ones, and there are a lot of average ones. And the work that both Bill and Amanda have done for me and for Silicon Quantum Computing already, without even being investors yet, is extraordinary. It's insane. And for us being primarily Australia based for the time being and needing doors to be unlocked for us, particularly in the US, which is something that these guys have done without any sort of question at all. As soon as you ask, they're on it straight away, is totally invaluable to businesses like ours. And it's just incredible. And so the time at which they call me to say, hey, look, we want to invest in the founder. Can you say some good words about us? I'll fly and I'll
this is for these investors to maybe invest in you. That's what I'm hoping too. But thank you. All right. Yeah.
So full of admiration.
Thank you.
Guys.
Peter, from your chair of Quantum Australia, like how did you find them, and can you give a little macro view on what's going on here and why this is so exciting? Why we're so excited about it?
So do a few things. Firstly, I'm not part of Quantum. I'm not Michelle. It's interesting though, because Michelle is on the Quantum Australia board, which I chair. So it's a not-for-profit board set up by 13 universities, the federal government, to raise Australia's position in the quantum technologies, everything from sensing to cyber to the whole lot. We get asked very interesting questions at public events. So first, we always get asked, are companies like these destroying the environment in a parallel universe? So that one we get a lot, which Michelle handles really well. We get a lot of questions about Big Bang Theory and Schrodinger's cat. So the actual science under that is true. It's correct. So with a quantum qubit, it can be on, it can be off, it can be both at the same time, and it can be something in the middle. So there's a huge leap of faith, which is why we all regularly rewatch Quantum for Dummies. But the real power in quantum computing is the power of doubling, which, if you double and double and double, because these things, there's 5 core modalities. One of them is on silicon. And so I think you can probably talk around a little bit, but one of the things Michelle pioneered was they flick a silicon atom off a silicon chip and replace it with a phosphorus, right? That one phosphorus atom becomes the computer switch. And so imagine how you can scale that, but also you can plug it into all those other silicon devices. But the power of doubling, someone told me today, actually a leading professor in quantum, she's been in the field since 1999. She said if you just take paper and you fold it, I think it's 256 times you reach the moon. You double it one more time, you reach Mars. So the power of doubling is immense, and the power of quantum computing is in doubling. So as these things get more powerful, and they do tackle really complex problems. So the 3 core areas, with 3 or 4, we're seeing for the quantum industry is medical research. So you can do a lot around pretty much everything in your body, around STEM modeling and all sorts of things. So John Barrington, just wait, most of you will know John. It's not announced yet, but John will be joining our board next week. And John used to chair the Perkins Medical Institute. There's a lot in that area. The other areas in defence. So if you know AUKUS, the massive project, Pillar 2, quantum is a core pillar. One of the leaders in quantum research is NASA AIM. So there's a significant amount of work being done on quantum. Mining already uses a huge amount of quantum in sensing, so undercover, deep cover, and same with medical for imaging. The other question I get asked all the time, I think it was the first one Bill asked, is will it break Bitcoin? It's probably relevant for a lot of people in the room. I'm not going to answer it because I'm not a quantum person. I'll let you figure that out. But the power is significant, and it will tackle problems that we cannot tackle today in logistics, in medical, in many areas. And really the question becomes, when can you do it at scale? And one of the things with a modality that can be on, off, or in between is you can set it to on and then turn around and it's moved itself. And so error correction is the big challenge. When can they go do that? So the reason I introduced Michelle to you guys was many of the things Bill talked about, I saw in Michelle and what they're doing. And she's not out there promoting herself, and she's basically just building a great business. And so so that was really the introduction. Again, I thought it was 30 minutes. But it's interesting. Most people think quantum computing is so far off, and parts of it are, but there's a lot happening now, and which you can probably talk a bit more to.
Yeah, I think one of the special things about SQC or silicon quantum computing to take away is that atoms make the best qubits. And I don't think that's a sort of contentious thing to say. All of, well, many at least of the leading quantum computing companies on any and all metrics are people using atoms as their qubits. But SQC and what Michelle has pioneered means that we are the only company in the world that can operate, can physically manufacture, but operate atoms placed within a pure silicon wafer as our qubits. And, those words might not be extraordinary, but if you think about the fact that the world has already scaled up one form of computing in silicon, and the fact that our business, or Michelle's business, is the only one that can use the best quality qubits in a manufacturable platform is, absolutely extraordinary. And I think, one of the key advantages.
I thought, because we're running out of time, I thought maybe if you could just tell us your last product, what can it do and how far off is it?
So the fully error-corrected commercial scale quantum computer, on our roadmap, we see that being delivered in 2033. And indeed, this is, one of the things which DARPA is so excited about. And I think, the use cases that are on the table for that are for sure breaking RSA encryption, which is a problem for cryptocurrencies. But I think, for us as a company, we don't necessarily think about those catastrophic use cases nearly as much as we think about the use cases which can drive huge value. So one of the algorithms which we've been looking into a great deal is one that looks at synthesizing a catalyst which helps to break down the nitrogen triple bond as part of the fertilizer production process, which in itself takes up about sort of 2.5 to 3% of the world's energy to make fertilizer at the moment. And so if you can synthesize something organic which can help with that process, that's hugely valuable in an economic sense, but also in an impact sense. So, that's where we tend to focus on.
Great. I know we're way over. I do see that it's windy outside, and I do see Bill he's either checking emails or checking the wind forecast. I would bet it's the wind forecast. I do. In very briefly, what did you see in them? And then we'll just say thank you to everyone for coming. Especially thank you to the Vault ladies. Thank you to Lucy from Space Draft, who really helped to make all of this happen. Thank you, Gordon Cole, for welcoming us to country, and to Lars and to everyone who came. But Bill, why don't you close it just briefly on what you saw, why you're excited, and then we'll get out there. If anyone wants to kite with us, we're going to try to do some kiting.
All the way
Afternoon.
back to 1993, a friend of mine put a bunch of money into D-Wave and became chairman of the board and asked me to help him out. And I did a deep dive even at that time into quantum, and I've kind of followed it, since that time, which is 30 odd years. But there are many what's called modalities, different approaches to this, and they're also, to me, loose. Like, there's too many variables in that stuff, and I think a lot of bringing a complex technology to life, it's like kite surfing. It's the elimination of one variable at a time, and if you can get it down to just a few, you have a much better probability. And what he's talking about, a silicon platform, that is such an evolved technology. I mean, it's constantly changing, of course, and every 2 years there's a new, geometry from TSMC, et cetera. But the approach just made a lot of sense to me. I've been around 3 or 4 different generations of types of transistors, from bipolar to MOS to CMOS, whatever. And what we whiteboarded, because that's what I wanted to know. When I went up to the whiteboard with Michelle, we were basically drawing the evolution of transistors and how atoms flow in silicon, and I just wanted to understand how the bits were trapped in the silicon and how you would, how you manufactured them, how you move them, and the approach seems very logical to me. And actually they're making some at small scale. So in software also, the software products that I find, I always push on my entrepreneurs. You have to solve a problem, make it low friction to use, and highly replicable, highly scalable. That's all you have to do. That's Canva, that's Zoom. I mean, there's a lot of other stuff too, but from product perspective, and that applies to hardware too. And I think this approach, it relies more on known quantities assembled than all these other things with like lasers and all kinds of things trying to, you can get it to work once and all these other things that look prototypey to me. This method looks very achievable. And I think, and it was interesting, Simon Segars, who was the CEO of ARM, he was employee 13 of ARM, I think, and they're from the late 70s or something. Same thing, old crusty silicon guy, and he jumped in as chairman of the board, and I think I had a similar reaction to him because we both have been around silicon for 30 or 40 years. And it seems very doable. I mean, it's not easy to do. The machinery part is like crazy. You got to operate in these vacuums and all that. It's a lot of manufacturing stuff that's interesting, but none of it is rocket science. So it seems very practical, where a lot of the other stuff is a little bit rocket science and maybe 3 or 4 of the other things. So that's why I think it's possible.
Awesome. Well, thank you so much, everyone, for coming. Really appreciate your time. Thank you again to the Vault and Space Draft for helping to make all of this happen today. And I'm here for I think we have the room for another half hour if anyone has questions. Otherwise, I understand the Australians kind of go into Christmas and kind of do not come back until February. So I've been told if nobody's going to talk to you in the next month, but I continue working. So if anyone wants to talk to me on Zoom, I'm here, or we can pick it up in the new year. But thank you everyone for coming. Appreciate your time.